Assalamu alaikum students. I hope you are fine. We continue exercise 2.6 with question number 6 in which we learn about the free properties related to the complex numbers. And these properties are given in these 6 different parts. Let's prove these properties one by one. Start with part 1. To prove this, we need two different things. First of all, for the left hand side we need the sum of the complex numbers, and in the right hand side we need sum of the complex conjugate of the given numbers. Let's begin with it. We take left hand side first. Z plus W whole bar is required for this. First of all, we have to add Z and W, mean the given complex number. 2 plus 3 iota plus 5 minus 4 iota. We open the brackets. 2 plus 3 iota plus 5 minus 4 iota. Real parts are added. 2 plus 5, 7. Signs are different, so imaginary coefficients are subtracted. Minus 4 plus 3 minus iota. Z plus W we have. At the left hand side we need conjugate of the sum of the complex numbers. So therefore we take the conjugate of the both sides. So Z plus W whole bar is equal to 7 plus iota. We already learned that conjugate is obtained by changing the imaginary coefficient. Hence we name this as equation 1 for reference. We take the right hand side in which we are required sum of the complex conjugate of Z and W. Z bar is equal to 2 minus 3 iota. We change the sign of the imaginary coefficient. And now we get the conjugate of the W, and that is 5 minus becomes plus 4 iota for conjugate. Now we add these. Z bar plus W bar is equal to 2 minus 3 iota plus 5 plus 4 iota. We open the brackets. 2 minus 3 iota plus 5 plus 4 iota, as the plus sign is outside the bracket, so therefore no change. 2 plus 5 real parts are added. 7. Imaginary coefficients are subtracted as their signs are different. 4 minus 3 plus 1 iota. 1 is understood, therefore we do not write over there. Z bar plus W bar. We got the result of the right hand side. We name it as number 2 for reference. So thus from equation 1 and 2, by the comparison we get what? Right hand sides are same, and according to the transitive property as learned in the lectures of the properties of real number. So according to transitive property, if one side of the two equation is same, then the other sides are equal, and that's why we write Z plus W whole bar is equal to Z bar plus W bar. So first part is proved. Now we move to the second part, and that is Z minus W whole bar is equal to Z bar minus W bar. So part 2. Z minus W whole bar is equal to Z bar minus W bar. For proof, we take the left hand side first. Z minus W whole bar, And for this, we need the difference of the complex given numbers. 2 plus 3 iota minus 5 minus 4 iota. We open the bracket. 2 plus 3 iota minus plus minus 5 minus minus plus 4 iota. Real parts are subtracted as the signs are different. So minus 5 plus 2 equal to minus 3 because the bigger value is 5 and its sign will be carried. So 3 iota plus 4 iota, signs are same. We add them. 7 iota. Z minus W. As in the left hand side we require the conjugate. So we take the conjugate of both sides and we get minus 3 minus 7 iota as the basic requirement to get the conjugate of the complex number is to change the sign from plus to minus. We get the result of the left hand side, we name it as equation 1. Now take the right hand side in which we require z bar minus w bar. For this sake, first of all, we have to find out the conjugates of the given complex numbers. So z bar is equal to 2 minus 3 iota by changing the sign of imaginary coefficient of z. W bar is equal to 5 plus 4 iota. Now we can find the difference. Z bar minus W bar is equal to, we put the values, 2 minus 3 iota minus 5 plus 4 iota. We open the brackets. 2 minus 3 iota minus 5 minus plus minus 4 iota. Real parts are subtracted. Minus 5 plus 2 we get minus 3. As the signs are same for imaginary coefficient, minus 3 minus 4 is equal to minus 7 iota. We name it as equation 2 for reference. Z bar minus W bar, we got the results. And as according to transitive property, we get what? We see that the right hand sides are same, I mean one side is same, then the other sides will also be equal. So therefore by comparing equation 1 and 2, that is from equation 1 and 2, z minus w whole bar is equal to z bar minus w bar. And that is for the proof of the second part given in the question. Z minus w whole bar is equal to z bar minus w bar. We continue with the part 3 of question number 6. And in this we observe the properties related to the product. Z w whole bar is equal to z bar w bar. In proof, we take the left hand side first. Zw whole bar is equal to question mark. For this we need the product of z and w, the given complex numbers. We put the values. 2 plus 3 iota, 5 minus 4 iota. We use the simple linear method of multiplication in which 2 is first multiplied by 5 minus 4 iota and 3 iota is multiplied by 5 minus 4 iota. 2 5s are 10, 2 4s are plus minus minus, 2 4s are 8 iota, plus 3 5s are 15 iota, minus 3 4s are 12 iota into iota, iota square. 10 imaginary coefficients are subtracted as these like terms have different signs. So plus 15 minus 8 is equal to plus 7 iota. Minus 12, we put the value of iota square, that is minus 1. 10 plus 7 iota minus minus plus 12. And we get what? 10 plus 12, 22 plus 7 iota. We got ZW. As the left hand side we need its conjugate, so we take conjugate of the both side, and what we get? 22 minus 7 iota. We name it as equation 1 for the reference. Now we take the right hand side, in which we are required to find the product of z bar and w bar. For this we need the conjugate of these two. Z bar is equal to 2 minus 3 iota, whereas w bar, mean conjugate of the w, is 5 plus 4 iota. Now we multiply these two, mean conjugate of the z and w. We put their values, 2 minus 3 iota, 5 plus 4 iota. We use the simple linear method of multiplication. 2 is multiplied to 5 plus 4 iota, and then the second term minus 3 iota is multiplied to 5 plus 4 iota. 2 5s are 10 plus 2 4s are 8 iota, minus 3 5s are 15 iota, minus plus minus 3 4s are 12 iota into iota becomes iota square. 10 is carried, imaginary coefficients are subtracted as the signs are different. Minus 15 plus 8 is equal to minus 7 iota minus 12 iota square. We put the value minus 1. 10 minus 7 iota minus minus plus 12. 12 plus 10, 22 minus 7 iota. So we get the product of the conjugates of the complex numbers which are given. We name it as equation number 2 for reference, and by the comparison what we get, we see right hand sides are same, 22 minus 7 iota. So according to transitive property, we write the left hand sides are equal. So therefore we compare these two equations and write as from equation 1 and 2, ZW whole bar is equal to Z bar W bar. Hence it is proved ZW whole bar is equal to Z bar W bar, and that is for the part 3. Now we move to the part 4 of the question number 6. In this we observe the property of the complex numbers related to division. So let's begin to prove. Part 4. We are required to prove the conjugate of the quotient of z and w is equal to the quotient of the complex conjugate of z and w. So let's begin the proof. We take the left hand side, that is z over w whole bar, and that is to be required. For this, first of all, we have to find out the quotient of z and w, the given complex number. So let's begin. Z over w is equal to, we put the values, 2 plus 3 iota over 5 minus 4 iota. As we already familiar about the solution of such a rational form of complex numbers, we multiply the conjugate of the denominator and divide to rationalize the denominator to get the standard form of complex number. So 2 plus 3 iota divided by 5 minus 4 iota multiplied by 5 plus 4 iota divided by 5 plus 4 iota. Numerator is multiplied to the numerator. 2 multiply 5 plus 4 iota, simple multiplication, plus 3 iota, 5 plus 4 iota. Whole divided by, we apply formula on denominator. A minus b into a plus b is equal to a square minus b square. So value of a is 5, value of b is 4 iota. 2 5s are 10, 2 4s are 8 iota, plus 3 5s are 15 iota, plus 3 4s are 12 iota square. 5 square becomes 25 minus 4 square is equal to 16 iota square. We have in denominator. 10 plus 8 plus 15, 23 iota. As these are like terms, so their coefficients are added. 12, we put the value of iota square, that is minus 1 whole divided by 25 minus 16 iota square means 16 into minus 1, we put the value of iota square. 10 plus 23 iota minus 12 divided by 25 plus 16 in the next step. 10 minus 12 will become minus 2 plus 23 iota, and in denominator we have 25 plus 16, that is 41. Hence, by applying the inverse action of taking LCM, that is minus 2, we write the denominator with this both numerator, minus 2 over 41 plus 23 over 41 iota, and that is how we get the quotient of Z and W. As in the left hand side we required its conjugate, so we take the conjugate of the both sides and we get what? Minus 2 over 41 minus 23 over 41 iota, and we name it equation 1 as a reference. Now take the right hand side, in which we are required to find out the quotient of the conjugate of the complex numbers. For this we write first Z bar, and that is equal to 2 minus 3 iota, and the conjugate of the W is W bar 5 plus 4 iota. Now we find the quotient. Z bar over W bar is equal to 2 minus 3 iota over 5 plus 4 iota. We rationalize the denominator by multiplying and dividing by the conjugate. 2 minus 3 iota whole divided by 5 plus 4 iota multiplied by 5 minus 4 iota divided by 5 minus 4 iota is equal to, numerator is multiplied to the numerator. 2 multiply 5 minus 4 iota minus 3 iota is multiplied to 5 minus 4 iota whole divided by, we apply formula on the denominator, we get what? 5 square minus 4 iota square, because a plus b into a minus b is equal to a square minus b square. 2 5s are 10 minus 2 4s are 8 iota minus 3 5s are 15 iota minus minus plus 3 4s are 12 iota square, iota into iota, iota square. 5 square is equal to 25 minus 4 square 16 iota square. 10 we carry in the next step. Signs are same, we do addition for these like terms. Minus 23 iota plus 12, we put the value of iota square, that is minus 1. We get 25 minus 16, we put the value of iota square, that is minus 1. So we move to the next step and we get what? 10 minus 23 iota plus minus minus 12. 25 minus minus plus 16. 10 minus 12 is equal to minus 2 minus 23 iota whole divided by 41. And in the next step, we apply the inverse action of taking LCM. Minus 2 over 41. We write 41 along with both terms of numerator. Minus 2 over 41 minus 23 over 41 iota. And that is the final result of Z bar over W bar. We name it as equation number 2. Hence, by comparing the right hand side of these two results, means Z over W whole bar, Z bar over W bar, the right hand sides are same. Right hand sides are same. So therefore, left hand sides are equal according to transitive property of equality of real numbers. From equation 1 and 2, we get Z over W whole bar is equal to Z bar over W bar. Hence, that is proved. So that is the proof of the part 4 of this question number 6. Let's do the part 5 of question number 6 of exercise 2.6, in which we are required to find that 1 over 2 into Z plus Z bar is the real part of Z. So we have to prove for this. So part 5. One over 2 into Z plus Z bar is the real part of complex number Z. For proof, we have to find out the value of 1 over 2 into Z plus Z bar. And for this, we need the conjugate of the Z, and that is Z bar is equal to 2 minus 3 iota, and that is obtained by changing the sign of imaginary part, that is plus 3 in the given complex number, and we change it as minus 3 over here. Now we put the values for 1 over 2 into Z plus Z bar. 1 over 2 into the value of Z is 2 plus 3 iota plus the value of Z bar is 2 minus 3 iota. Now we open the brackets. First, according to BDMAS rule, we open the parenthesis. 2 plus 3 iota plus 2 minus 3 iota. 1 over 2. Like terms having different signs are cancelled. So 2 plus 2 is equal to 4. And we get what? 2 1s are 2 and 2 2s are 4. We get the value for 1 over 2 into Z plus Z bar is equal to 2. As we know that real part of given complex number Z is 2. We observe from over here. That is the real part. We name this 1 and 2 for reference. From 1 and 2, we observe the right side is same. We observe the right side is same, so therefore we can equate the left hand side by the transitive property, and that is 1 over 2 into Z plus Z bar is the real part of Z. and hence that is proved 1 over 2 into z plus z bar is the real part of z. Let's move to the part 6, in which we are required to show that 1 over 2 iota into z minus z bar is the imaginary part of z. So let's prove it. Part 6 to prove 1 over 2 iota into z minus z bar is the imaginary part of z. For proof, we need to find the value of 1 over 2 iota into z minus z bar first. And for this sake, we need conjugate of the given complex number z. And that is z bar is equal to 2 minus 3 iota. Now we put the values for 1 over 2 iota into z minus z bar is equal to 1 over 2 iota into, we put the value of z, that is 2 plus 3 iota minus value of z bar 2 minus 3 iota. We open the bracket according to Bede-Mass rule, first parenthesis. So 2 plus 3 iota minus 2 minus minus plus 3 iota. Two minus 2, like terms, different signs, cancel. 3 plus 3, 6 iota we have. 2 1s are 2, 2 3s are 6, and iota is cancelled by iota, and we get what? 3. 1 over 2 iota into z minus z bar is equal to 3. As we know that imaginary part of z is equal to 3 by the given complex number, we observe that imaginary part is 3 over here. So we name 1 and 2 for reference, and by the comparison right hand side same, so we can equate the left hand side by the transitive property. So from 1 and 2, what we get? 1 over 2 iota into z minus z bar is the imaginary part of z. Hence, that is proved 1 over 2 iota into z minus z bar is the imaginary part of the given complex number z. And that is for the last part of the question number 6. Thank you.